Right, in this video, we're going to be using theorem 7.1.1 to find the Laplace transform of some functions here. We'll need to do some basic algebra and things sometimes to be able to do this. But let's start off with theorem 7.1.1 and talk about the Laplace transforms of these basic functions. So our first Laplace transform that you should know is that the Laplace transform of 1 is equal to 1 over s. This is the rule that we're going to use for the Laplace transform of any constant. Remember that Laplace transforms are integrals and inherit all the properties of integrals, so we can pull constant multipliers out front. So you can look at that as like the Laplace transform of C is going to be C over S, because you're going to have that constant multiplier that gets pulled out front and then multiplied into the numerator. So you can think about all these with constant multipliers and things as well that won't change the rule. You'll just multiply by that constant. Okay, second rule here, the Laplace transform of t to the n is going to be, and that's an n factorial in the numerator. Hopefully you've dealt with factorials before this and know what that is. If not, go look that up. We'll be using it a little bit here later, but this is not the place for me to teach that to you right now. And the denominator is going to be s to the n plus 1, and this works for n's of 1, 2, 3, so on and so forth. We don't, it actually works for n equals 0 as well, which is this rule. We don't normally think of t to the 0 being 1, but 0 factorial is 1, s to the 0 plus 1 is s. So this first rule is a special case of the second rule. We're going to sometimes think of a different rule in between these rules for the Laplace transform of t, where n is 1 just because that happens so often. 1 factorial is 1, s to the 1 plus 1 is 2. So we may think of, even though it's not in this theorem, we may think of this rule separately here, that the Laplace transform of t is 1 over s squared. So I'll just write that off to the side over there so you have that one, since we use it so often. It is a separate rule in your chart in the back of the book, which is in Appendix C, I believe. Let me take a look at that to make sure that that is correct. Yes, Appendix C is your list of all of your Laplace transforms. And there's also, if you have the hard copy of the textbook, then there is a chart in the, let's see if it's in the front or in the back, in the very front of the textbook. So you have a table of Laplace transforms as soon as you open the textbook. That's inside cover and the first page. So I'll keep that out so I can reference some of those numbers here. So this is number 1 on that chart. This is number 2 on that chart. This is number 3 on that chart. Skip down some, and we have, this one is number 7 on the chart. This one is number 8 on the chart. This one is number 11 on the chart. Then these are 14 and 15 on that chart in the front of the textbook, or in Appendix C. So next one here, part C, of theorem 7.1.1, Laplace transform of an exponential function in the form of e to the at is equal to 1 over s minus a. Then we have d Laplace transform of sine of kt is going to be equal to, notice that you have a constant k, which is this constant multiplier in front of t in the numerator, s squared plus k squared in the denominator. Cosine Laplace transform of cosine kt is going to have the same s squared plus k squared in the denominator, but now you're going to have an s in the numerator. So watch out for those. That sine has a constant in the numerator, cosine has the variable s in the numerator. Hyperbolic sine, the Laplace transform of hyperbolic sine of kt, again, have that constant k in the numerator, but now our plus sign changes to a minus sign. So we have s squared minus k squared when we go into the hyperbolic world here. And for part G, Laplace transform of hyperbolic cosine of kt, again, we have our s since it's cosh, but we have that denominator of s squared minus k squared. Okay, let's go ahead and look at some problems starting with number 19 from the textbook. And it asks us to find the Laplace transform of t to the fifth. So that's going to be 5 factorial over s to the 5 plus 1. So 5 factorial is going to be I'm sorry, I wrote the wrong one down. Let's try again. 2t to the fourth. So that's 2 times the Laplace transform of t to the fourth is equal to 2 times, then that's going to be 4 factorial over s to the 4 plus 1. So 4 factorial is 4 times 3 times 2 times 1. It's s to the fifth. 8, 24, 48 is my numerator over s to the fifth is my transform there. If you want to see that other one, that was number 20, I'll go ahead and do it. T to the fifth is equal to 5 factorial over s to the 5 plus 1. 5 factorial is 120. And you can do that in your TI-83, TI-84 calculator with the math menu, arrow over to, I believe it's it's either NUB or PRB, but it's one of the first options there is the factorial exclamation mark in there. It's in your math menu, either under NUM or PRB. So take a look for it in there. If you want to just have your calculator calculate the factorials for you, or you can use the definition that n factorial is equal to n times n minus 1 times n minus 2 times so on and so forth until you get down to 1. And by definition, 0 factorial is equal to 1 as well. So we don't have negative factorials. If you we don't do fractional factorials. If you get those types of numbers and need something similar to the factorial function, you'll use the gamma function, which is something that you will talk about possibly in this section. If your teacher wants to do those examples with you, great. I'm not going to do any examples with you of that, but it is in your textbook if you want to take a look at that. So inheriting properties from integrals where we can split a sum or difference. Then I'm going to pull the constant multiplier out. And we already talked about this one here, and we talked about this one here being something that was just 1 over s squared. So we end up with 4 over s squared minus 10 over s. Let's go ahead and look at number 23. That's f of t is equal to t squared plus 6t minus 3. So we want Laplace transform of this. So that's Laplace transform of t squared plus 6 times Laplace transform of t minus 3 times the Laplace transform of 1. So that's going to be 2 factorial over s to the 2 plus 1 plus 6 over s squared minus 3 over s. 2 factorial is 2 over s cubed plus 6 over s squared minus 3 over s. Number 25 is f of t is t plus 1 cubed. We don't know how to deal with something that's called a convolution yet. That is a composition of functions. So we're going to have to break this down into t cubed plus 3t squared plus 3t plus 1. Do that off to the side if you need to, if you don't know the binomial theorem, to help you expand that as quickly as I just did. But let's go ahead and write this as Laplace transform of t cubed plus 3 times the Laplace transform of t squared plus 3 times the Laplace transform of t plus the Laplace transform of 1. And so that's going to be 3 factorial over s to the 4th plus 3 times 2 factorial over s to the 3rd plus 3 times 1 factorial over s to the 2nd plus 1 over s. 3 factorials, 3 times 2 times 1 is 6 over s to the 4th. 3 times 2 times 1 is 6 again over s to the 3rd. 3 times 1 is 3 over s squared plus 1 over s. And I'm going to do a few more here. Let's go on to number 27. Laplace transform of 1 plus e to the 4t. So that's going to be Laplace transform of 1 plus Laplace transform of e to the 4t is going to be 1 over s plus 1 over s minus 4. That was 27. Laplace transform of 1 plus e to the 2t squared. Again, we don't know how to do convolutions yet, so let's go ahead and expand this into 1 plus 2 e to the 2t plus e to the 4t. So that's going to be Laplace transform of 1 plus 2 Laplace transform of e to the 2t plus Laplace transform of e to the 4t is 1 over s plus 2 over s minus 2 plus 1 over s minus 4. Let's go ahead and look at number 31 here. And that'll wrap things up for us for this section. The Laplace transform of e 4t squared minus 5e to the 3t. So the Laplace transform of 4t squared minus 5 sine of 3t. So that's going to be 4 Laplace transform of t squared minus 5 Laplace transform of sine of 3t. And so this is going to be 4 times 2 factorial over s cubed minus 5 times, and then k value of 3 over s squared plus k squared. So that's 4 times 2 is 8 over s cubed minus 15 over s squared plus 9. And we'll leave it there. We'll come back next time to talk about inverse Laplace transforms in 7.2. And that's kind of like how you can use the right-hand side of the table if you can make it fit that form to go backwards to what f of t was. So if we have capital F of s, just write it here, inverse Laplace transform of capital F of s, where I should put the braces around this, where capital F of s is the Laplace transform of a function we know, then we can write that as lowercase f of t, kind of like how you can differentiate a antiderivative to get the original function, that same kind of idea. So there we go. We will be doing that in the next video here, and see you for the next video.